So, a very good afternoon, madam. My name is Ong Zhen Yang, and today I'll be sharing the topic for my instrumental and measurement integrated project, with it being smart parking system, which is solely based on the topic that I've conducted in my ETP this semester. So, moving on, up next we have problem statement. So, problem statement just basically share about the problems that I have identified based on project background that is supported by the data and trends that is shown in on my project background. So for the first point, we have traffic congestion. Now, based on the research conducted by Donald Shoup, it revealed that approximately 30% of urban traffic isn't about drivers driving to a destination, but it's rather about people just cruising around looking for parking lots. And this creates an unnecessary gridlock. And for point number two, we have economic and time loss. And according to INRIX's data, the average driver wastes about 17 hours a year just in searching for spots, and this isn't just annoying, but it is also costing billions in field and lost productivity. And for the third point, we have inefficient space utilization. Now, traditional parking lots suffer from uneven occupancy, where drivers crowd the visible slots near the entrances of popular slots shops, while hidden spots, on the other hand, simply just sits empty because no one knows they are there or available. And for the fourth point, based on the perspective of a stakeholder or a business owner in this case, manual parking system causes low turnover rates. When cars occupy and maneuver around the parking vicinity inefficiently and slow, new customers simply just can't find a place to park quickly, which directly limits the number of customers a business can handle and serve in a day. So that's it for the four problems. And up next, we'll move on to sensor selection. All right, so for the first part for sensor selections, I've selected these three sensors: ESP32 camera, ultrasonic sensor, and infrared sensor, where the variable that these three sensors will be measuring are distance. So for ESP32 camera, it's measure distance in the sense that it will try to detect to optimize the frame of the picture that is taken, where it will factor in the width and the length of the picture. And the second part is ultrasonic sensor, where it will measure distance between the gap and the sensor. And for infrared sensor, it's also technically as same as the ultrasonic sensor, where it will measure the distance between the sensor and the car, so that it would be able to trigger the camera. So that's basically it for this part. Let's move on to the next part, where I will dive deeper in the depth on how I select the best sensor for this project. Now, diving deeper into the sensor selections part, in this part, I would like to share how would I be evaluating these three sensors, and based on what criteria would I be evaluating it upon. Now, for the first criterion we have is cost. This is the most important criterion because I had to prioritize the given budget of 500 ringgit for my ETP project. And based on the cost, the cheapest one we have here is the infrared sensor, which can be simply bought at 2 ringgit per unit, followed closely by the ultrasonic sensor, which is priced roughly around 3 to 5 ringgit per unit. And lastly, the most expensive one we have here is the ESP32 camera, which is priced around 40 ringgit per unit. And for the second criterion we have here is functionality. I started with the ESP32 camera because it offers the most advanced capabilities. It's able to capture visual data, allowing us to use Google Cloud to infer presence, estimate distance, and even determine the vehicle's identity. In comparison, the ultrasonic sensor is strictly a measurement tool. It uses sound wave and time of flight calculations to give us a specific distance value, but nothing more. Finally, the infrared sensor is the most limited. It uses light refraction for a simple on and off detection, basically acting as a digital switch without any complex data output. And for the last criterion we have here is accuracy and reliability. For the ESP32 camera, the reliability is quite unique because it depends on image clarity and lighting. While subjective, this is the most powerful because it allows us to filter out false positives like a stray object that might trick other sensors. On the other hand, the ultrasonic sensors is objectively the most precise one, where because it has a tiny error rate of only 0.03 centimeters, making it excellent for pure measurements, And lastly, for the last one, we have infrared sensor, which is not designed for precision at all. It is built for speed and close range detection, making it reliable only as a trigger, not a measuring instrument. So this comparison clearly showed the trade-offs between cost, capability, and functionality, and it will lead to my final decision in selecting the most appropriate sensor for this project. So after weighing the pros and cons, I've decided that the ESP32 camera is the most suited sensor for this project. While the other sensors are useful, the camera is the only one that truly empowers the smart aspect of this system for three specific reasons. Firstly, dual functionality. Unlike the simple IR or ultrasonic sensor that can only detect if an object is blocking or present in a spot, the camera is able to perform two critical tasks simultaneously. It's able to confirm whether a spot is occupied, and it's able to identify the specific vehicle that is parking or present in front of the lot there. This allows for features like security verification that the other sensors simply cannot provide. And for point number two, high functionality at low cost, which in turn would also mean cost efficiency. Now, at first glance, it may seem more expensive than a simple sensor. However, the ESP32 camera is an all-in-one solution. It eliminates the need for a separate microcontroller or an external Wi-Fi module because everything is already built in it. This reduces the overall system complexity and actually makes it highly cost-effective for the features we get. And for point number three, enhanced cloud processing. By choosing this sensor, we can offload heavy data analysis to Google Cloud, where this allows us to leverage powerful Wi-Fi modules to redefine and process images for maximum precision, far exceeding the accuracy capabilities of a standalone hardware sensor. And for these reasons, I also think that the ESP32 is also the core component for my prototype. So for this part, sensor implementation, I would like to briefly share upon how was the prototype constructed and briefly introduce the prototype. So as you can see in both pictures, this is the car park that I have built, where we have an infrared sensor to the utmost front, and right above it is the ESP32 camera. Right beside it, there's the barrier on its right, and the sensor in the box, that's actually an ultrasonic sensor. So this is basically the entire parking system, where the infrared sensor would trigger the camera and the ultrasonic sensor would detect the distance between the sensor and the car, and the barrier would open and close to allow the car to enter. So that's basically it. Let's move on to the next part. Now, moving on for this part, I'd like to share on how does the selected sensor ESP32 camera is able to verify whether the car has arrived at the correct distance or not. To solve this, I implemented a technique called optical validation, where if you look at scenario A on my left, the vehicle has reached too close, less than 0.5 meters away approximately, and because it is outside the camera focal range, the image becomes blurry and the license plate is cropped. And as a result of that, the Google OCR fails to read the text and the system effectively says invalid parking position. It refuses to process this image. Now, let's compare to scenario B to my right. Here, the vehicle is in its optimal zone between 0.5 meters and 1.5 meter. This image is clear, and the license plate is sharp, as shown. Because the image clarity is high, the OCR successfully extract the text as UTP-14, as shown in the third picture at the furthest right. And this is also how the parking system is able to identify respective users. So that's it for this part. Let's move on to the next one. And to close this presentation, I would like to make a quick conclusion. So in conclusion, this smart parking system is just not about just finding a spot, but it is about reclaiming the 17 hours a year that we have wasted in traffic in finding a parking lot by combining the affordability of simple sensors with the intelligence of the ESP32 camera and Google Cloud. So we can build a city that's just not bigger but truly smarter. Thank you for your time, madam, and I hope you enjoyed my presentation. Thank you.